Okay, so in the last class we learned that if you look at cake filtration, so there's a the liquid that flows through two resistors that are in series. That means it. So initially you have the fluid that is flowing through a filter cake, plus it is also flowing through the filter medium, and we learned that the total pressure drop delta P is equal to the summation of the pressure drop across the filter cake plus the pressure drop across the filter medium, right? And in this class what we are going to look at is how do we think about expressing delta Pc, that is the pressure drop across the filter cake, and delta Pm, which is the pressure drop across the filter medium, in terms of some of the measurable properties such as the flow through the filtrate flow rate, the viscosity of the filtrate, the properties of the particles and things like that. Okay. So first what we will do is we will start with thinking about the pressure drop through the filter cake. That is, we are going to talk about how do we relate delta Pc to the measurable parameters. What you are looking at is a diagram, okay, where this is basically a section through a filter cake and the filter medium at some time t, from the start of filtration. Okay, that is, you at time t is equal to 0, you do not have any filter cake developed. That means your this part is not there, right? So only thing that you have is only the filter medium, and during the course of filtration the filter cake builds up. At time t is equal to 0, what you have done is you have taken a cross section, and the figure basically represents that view. Okay, and so in this diagram, so the direction of flow is basically marked there. So that's a direction of flow of slurry, and that is the, if you want to call it as, that is a upstream end, right? And then the cake builds up and you have a filtrate that is coming out, that is the downstream. LC is the thickness of the filter cake, and that is measured from the filter medium, and A is the area available for filtration. So what it essentially means is, if I have, like, say, if this is my filter medium, right, and if the filtrate is flowing in this direction, the cross sectional area that is available for for the filtrate to flow through, that's A. And what we are going to do is we are going to look at a very thin section. So what is drawn here is a small section, okay, that is, I'm going to mark it now. So that's a very small thin section of dimension dl, that is, the dl is the thickness of the a layer of filter cake that I am considering, and this is basically located at a distance L. Okay, if the distance from the filter medium to that layer is capital L, and we are going to say that the pressure at that particular point, okay, is P. Okay, and what is shown in the figure is the pressure gradients. Now if you look at this thin section, okay, typically the velocity with which the filtrate flow through the filter cake are so low that you can essentially assume the flow to be laminar. Okay, so therefore you have so as I said, right, we are basically borrowing the concept from flow through packed bed, and we are trying to apply it to the flow through the filter cake. And the pressure drop across the filter across the packed bed, we said it has two terms, right? One is the laminar flow term and the turbulent flow term. So the laminar flow term basically goes with which is proportional to v or u in this case, which is the superficial velocity of the filtrate, and of course there is going to be a u square term that we are basically neglecting it because we are assuming the laminar flow, which is true because the velocity with which the filtrate flows through the filter cake are sufficiently low that you can assume the laminar flow conditions. So the other interesting thing to notice if you look at the pressure gradient, it's not linear, right? So it basically varies, okay, something like this, right? That's the line that is basically drawn. That's how the pressure drop varies, right? Now if you look at the conventional um, you know uh, packed beds, right? So you would expect the pressure drop to vary linearly with the length of the packed bed, right? If you because if you are if you are using certain kind of packing, okay, so what happens is that your the porosities are constants typically, and then your mu, which is the velocity, which is the viscosity of the fluid, that is constant. And if you're working with rigid particles, so essentially, so all these terms are essentially constants, and that basically gives rise to a linear variation of pressure with distance. However, that is need not be the case in the case of flow through filter cakes, because of which you essentially have not a linear variation, but a variation that looks more like a quadratic. Okay, the reason for that is that if you look at regions of the filter cake close to the filter medium, they are kind of subjected to a greater compressive force compared to the region that is the closer to the upstream, because of which there could be a spatial variation of porosity. Okay, that is one of the reason why there could be a non-linear variation. The other reasons could be that your view, which is the filtrate, the velocity with which the filtrate is flowing through the medium, that also could be spatially varying, depending upon what kind of system that you're trying to look at. Okay, so therefore this non-linear variation that you are seeing is essentially justified. So essentially what we are doing is, in this thin section we are going to say that the delta P by L, that is the pressure drop across this thin section. Okay, how does that vary with over the small distance dl, and we are basically retaining only the first part of the Ergens equation, that is the Kozeny-Kármán equation, right? Now what I can do is and as I said, the u is essentially defined as the superficial velocity of the filtrate, exactly in line with how the V naught bar was defined for the flow through packed bed. And what I can do is I can start with this expression, I can do some manipulations. Okay, so one of the manipulation that I can do is that instead of working with phi s square dp square, where phi s is the sphericity and dp square is the diameter of the particle that are part of the slurry which is being filtered, or the diameter of the particle that constitute the cake, I can replace the sphericity in terms of Sp by Vp, that is the specific surface area of the particle divided by the volume of the particle. And if I do that, I can replace phi s square dp square as Sp by Vp whole square divided by 6 square. Okay, and so the 6 square 36, therefore you have 150 divided by 6 square, that leaves out 4.17, right? And the superficial velocity of the filtrate is essentially defined as the rate at which the filtrate is collected at the downstream divided by the filtration area that is available. So in this definition, u is equal to dV by dt divided by A. V essentially refers to the volume of the filtrate collected from time t is equal to 0 until time t is equal to t. Okay, and once a particular volume of filtrate enters the filter cake, essentially the same volume flows to the entire filter cake. That means your whatever dV that enters, the same amount of volume is essentially flowing through the entire, if I basically split them into different strips, right? So dV essentially is same across all the strips that basically constitute the filter cake. Therefore your V by A is same for all layers. Therefore I can assume that u is independent of the length across which the filter the filtrate is essentially flowing. And the volume of the solids in the layer I can write this as A is the filtration area multiplied by delta L, that gives me the volume of the solid plus the liquids, in the filter cake, right, in the thin cross section, right. That is, so essentially A multiplied by dl gives me the volume of this thin section, okay. That multiplied by 1 minus epsilon will give me the volume of all the solids in the thin section. And if I want the mass, that is dm, that is the mass of the particle in the thin section, which is essentially this, the volume of the solids in the section multiplied by rho p, where rho p is the density of the particle that constitute the uh, that make up the of the solids in the filter cake, right. So therefore I can again simplify this equation further. So I have delta p here, okay, and I'm going to take dl to the right hand side, and I can write dl, okay. I had dl here, so if I want to write it as this term multiplied by dl here, right. So therefore I can express dl as dm divided by a times 1 minus epsilon into rho p, right. So one of the epsilon essentially cancels with this, so I'm basically left with 1 minus epsilon here. There is k1, there is mu u here, so I'm basically taking this as a constant k1, right. And of course sp by vp remains here, and I have dm that comes in, and there is a, that's here, and essentially epsilon cube remains here, and rho p. So essentially I'm basically expressing delta p in terms of delta m, right. Now so if you work with if you are doing filtration operation, and if you ensure that you are carrying out filtration operation under conditions where the pressure drops are very, very low, and if you are working with a slurry which contains rigid uniform particles, okay, all the prefactor including k1, mu u, 1 minus epsilon, sp by vp, rho p, all of these are constants, okay, and the only variable that I have is dm, okay. And you could ask a question as to what are the conditions under which you could have this each of the parameters that I'm mentioning as constants could vary. You can consider several cases. One of the example could be that if I have, like, say I'm working with a filtration process in which I, instead of having rigid particles that constitute the the slurry, if I have, like, say emulsion droplets, okay, which are essentially liquid droplets, right. And we know that as the filtration occurs, so I have the filter medium, and once these liquid droplets start depositing onto the filter medium, right, when the further filtration happens, these droplets could deform, right. Instead of them being perfectly spherical, they could take some shape like that, right. So therefore there could be variation of sp by vp, which we may have to worry, okay, if the particles that I'm working with are not rigid, okay. Similarly, if you have a slurry which contains loose flocks, for example, if the slurry consists of some kind of aggregates of particles, so what could happen is during the filtration process there could be some compaction of these aggregates, which could lead to changes in the porosity, okay. And of course you could also have cases where you could, so essentially if you're working with rigid particles, you could assume the rho p to be constant, okay. However, if you're working with something like microgel particles, which in such cases your rho p itself will not be a constant, microgel particles are particles where you have a rigid core, plus some hairy brush kind of a thing. There could be spatial variation of density. So therefore there are cases where you need not have the prefactor constant, okay. However, if you are working with slurries which contain rigid particles which do not deform during the course of filtration, I can assume all these terms could be constant. Therefore what I can do is I can get an expression for the pressure drop across the filter cake just by integrating this equation, okay, starting from, so my pressure at, so if I go back to the right, so if you have so P prime is the the pressure, okay, at the filter medium, right. So therefore I can integrate this expression going from P prime to Pa, where Pa is the pressure at the upstream end. Therefore I can integrate from P prime to Pa, dP is equal to, so all of this is constant if I am working with slurries containing rigid particles, and the mass of the cake that is deposited to begin with is 0, and then when the pressure drop is when the pressure is reached at, and I have a total of mc mass deposited, therefore I am going to have the integration from 0 to mc. Therefore this essentially gives rise to Pa minus P prime, which essentially is your delta Pc, which is the pressure drop across the filter cake, and so therefore this becomes mc, right. Now, so in this case I have assumed that the filter cake is incompressible, okay, and as I said, that is only true if I am working with rigid particles, right. Now so what I can do is I can define a particular quantity, which is what is called as specific cake resistance, okay, which essentially is I'm basically manipulating this expression, okay. I club a lot of constant together, so that's K1 there, okay, Sp by Vp whole square, that's here, okay, 1 minus epsilon, that's here, okay, and rho p into epsilon q, all of these things. So if you look at these parameters carefully, these are all the parameters that are specific to the kind of particles that are present in the slurry, okay, and essentially these are properties which depend on the packed bed, right. So epsilon is the porosity of the bed, right, and Sp, Vp and rho p are the properties of the particles. So all these constants put together are kind of clubbed together, and that's your alpha, and essentially you're left with delta Pc there, okay, and your A from here goes to the numerator, divided by, you have mu u, okay, and mc. So the other way to think about this specific cake resistance is that if you look up the flow through packed beds, right, so we had developed this expression delta P by L goes as 150 mu V naught bar into 1 minus epsilon whole square divided by epsilon q into phi s square dp square, right. Now I can plug a lot of these constants that are there, right. So all these constants I can plug them into one constant. I can write this as delta P by L is equal to mu V naught bar divided by something called as K, okay. K is what is called as permeability. K is what is called as permeability, which basically tells you in a way, one of the way to think about this would be that how much permeable the packed bed is for the flow of fluid, okay. And so if you look at this expression, this is what is called as a Darcy's law, okay, which essentially states that the flow or the superficial velocity essentially is directly proportional to the pressure drop across the bed, and it is inversely proportional to the viscosity, right. Now I can rework this, okay. I can say that your delta P basically is mu V naught bar divided by K by L, right, or is it okay. So now what I can do is in flow through packed beds, you define a resistance, okay, which basically goes something like this, okay. So
L is the length of the packed bed divided by this permeability. Okay, in this case, because we are talking about flow through, the cake, I can write this as Kc, that is the permeability of the cake. That essentially is defined as some kind of resistance. Okay, I'm going to call it as resistance because of the filter cake, Rc. Okay, so therefore the resistance because of the filter cake is defined as the length of the packed bed, or in this case the length of the cake, divided by Kc, where Kc is the permeability of the cake, right? Now, so therefore your Rm, which is L by Kc, basically goes as delta P divided by mu into V naught bar. Okay, so just look at the analogy of this expression with this, right? So I have delta Pc there, I have mu into u. Okay, therefore I can write this as delta Pc divided by mu into u whole divided by mc divided by a. Okay, this is the cake resistance, that is Rc, and because you have a flow through a filter cake here, so I would have to worry about what is the mass of the cake that is that is kind of deposited per unit area of the filter. Okay, so therefore your alpha, which is the specific cake resistance, is essentially defined as Rc, which is the resistance of the cake, which essentially is delta P divided by mu V naught bar in the case of flow through packed bed. So in this case, it's going to be delta Pc, which is the pressure drop across the filter cake, divided by mu times u, where u is the superficial velocity, divided by mc divided by a, which is the mass of the cake developed per unit area of the filter cake. Okay, that's the concept of the specific cake resistance. Now, of course, I can express alpha also in terms of phi a squared dp squared. That's basically going back to the starting equation. Only thing is, instead of k1, I'm going to have some other constant k2. Okay. Now, so therefore, so this is the expression that we have kind of developed, right? And as I said, right, so this expression that we are looking at, it may not be precise, okay, if the feed does not contain rigid particles. Okay, therefore your porosity, the constant K, Sp by Vp, they may vary from layer to layer, right? As I said, that if you look at the region close to the filter medium, okay, if there's a large cake that is developed, the region close to the filter medium, there could be a much more closer packing of particles compared to the region closer to the upstream, right? Or if you could have a case where you could have, if you have applied a larger pressure drop across the filter medium, there could be a compaction of the cake, which will lead to variation in the spatial variation in the porosity. Okay, therefore, okay, I may have to worry about non-linearity in such cases. However, for the case of incompressible cake, I can assume that there's a linear variation of pressure drop across the length of the bed. Okay, so similarly, in analogy with the definition of the cake resistance, we can also define the filter medium resistance. Okay, so we worried about mc by a. Okay, that's because we were talking about a specific cake resistance. Okay, which that means I would have to worry about what is the mass of the cake developed per unit area of the filter. But however, in the case of filter medium resistance, I don't have that term. That's because this is defined as the filter medium resistance. Okay, which is Rm, essentially goes as the length of the filter medium. That is, if you have a if Lm is the length of the filter medium divided by what is the permeability of the medium, that essentially goes as delta Pm, okay, which is the pressure drop across the filter medium divided by mu and u, right? So but of course, the delta pm, if you look up, the delta pm may also vary, right? Because if you could have a case, if you have if you have applied a larger pressure drop across the filter during the filtration process, what could happen is the larger the pressure drop can may force some of the particles through the filter medium, some of the solids through the filter medium. And depending upon the cleanliness, okay, if you have like some of the pores that are going to be blocked because of the presence of solids, okay, so these factors may change delta pm. But if you maintain the cleanliness, if you're working with reasonably smaller pressure drops, you can assume delta pm to be constant during the entire course of filtration process. However, delta pc would vary during the course of filtration. Okay, so therefore I can write the total pressure drop, that is delta p, is delta pc plus delta pm, okay, as the contribution from the pressure drop because of the cake, and the contribution that basically comes because of the presence of the filter medium. Now we have defined u, which is the superficial velocity, as dv by dt divided by a. You can relate mc, which is the mass of the filter, mass of the cake that is deposited, that is mc, in terms of v, which is the total volume of the filtrate collected from time t is equal to 0 to time t, okay, and c, which essentially is the mass of the solid particles deposited in the filter per unit volume of the filtrate. Okay, if I know these two quantities, mc essentially is the product of v times c. So this will have units of like say meter cube, okay, and c will have units of something like kg per meter cube. Therefore mc essentially will have units of mass, that is the mass of the solid particle that are basically deposited onto the filter cake per unit volume of the, right? So now so therefore instead of mc, I can replace mc with c times v, right? And so now what I've done is here, and of course I have u here, right? So u, I'm going to write it as dv by dt multiplied by 1 over a, right? And because I have delta p, right, delta p is equal to so I have delta p is equal to dv by dt multiplied by mu into mc alpha a plus rm, right? I have this. Therefore I can get this dv by dt to the other side, that becomes dt by dv, right? I'm going to get delta p to the right hand side, that you have delta p in the denominator, and mu remains wherever it is, and a also remains in the denominator. So essentially I'm recasting this equation as dt by dv is equal to mu divided by a delta p times alpha cv divided by a plus rm, right? Now so now I think I have an equation which is in a particular form, okay, which I can further reduce to suit the need of so we were talking about the constant pressure filtration and the constant rate filtration, right? So in the case of constant pressure filtration, what is done is you basically maintain a constant pressure drop across the filtration process, and then you basically look at how does the volume of the filter that I collect varies as a function of time. Okay, therefore I'm basically interested in to develop an expression in which t and v are my variables. So therefore I would, so what I have is this expression, okay. So what I know is because I'm working for a constant pressure filtration, my delta p is going to be a constant. Therefore in this expressions only variables are v and t, but I know the initial condition at time t is equal to 0, I do not have any filtrate coming out. That means your V is equal to 0, and the only pressure drop that I have is the pressure drop that comes because of the presence of the medium. Therefore, my delta P is essentially is equal to delta PM. Therefore, I can, so therefore my delta T by delta V at time t is equal to 0 is equal to mu multiplied by Rm divided by A times delta P, okay, plus the other term is going to be constant, is equal to 0 because V essentially is 0. Therefore, and I call this as 1 over Q naught. Okay, so therefore I can recast this equation as dt by dV is equal to 1 over Q, that is equal to Kc times V. So I have defined a constant Kc, which basically is your mu multiplied by C alpha, okay, that's the numerator, and divided by A square into delta P, and because delta P is constant, that basically is kind of included in this constant Kc. Therefore, dt by dV is equal to 1 over Q is equal to Kc times V plus 1 over Q0. Okay, I can integrate this equation further, and then if I put the limits that at time t is equal to at time t is equal to 0, but so I have the coordinates t is 0 0 and tv. Okay, that means at time t is equal to 0 I do not have any filtrate collected, and at time t is equal to 0 the total volume of the filter that I collected is essentially V. Okay, therefore this expression essentially becomes T over V is equal to Kc by 2 times V plus 1 over Q0, right? So what I've essentially done is your dt goes as Kc into V into dV plus 1 over Q0 into dV, right? So therefore if I integrate this, what I get is your 0 to t dt is equal to Kc into 0 to V into dV plus 1 over Q0 into 0 to V dV, right? So that this becomes your t is equal to Kc into V square by 2 plus 1 over Q0 into V. Okay, therefore I can divide everything by V. This becomes T over V, and 1 V essentially goes, and this also goes. So therefore you basically end up with an expression which is T by V is equal to Kc by 2 into V plus 1 over Q0. Okay, so therefore we have kind of developed a working equation which tells us how the dependence of T and V during the process of constant pressure filtration. One of the nice things about this expression is I can actually, if I perform experiments under constant pressure conditions, I can actually estimate what is Kc and what is Q0, and you can if you go back and look at what does Kc and Q0 depend on, the Kc depends on what is alpha, which is the specific cake resistance, and 1 over Q0 basically depends on is related to Rm, which is the filter medium resistance. Therefore what I can do is I have a framework to essentially calculate what is the filter medium resistance and the specific cake resistance, and you can also exploit the constant pressure filtration to say something about what is the type of the cake that is kind of formed during the course of filtration. So what I can do is I can conduct a number of constant pressure experiments. That means I basically maintain various pressure drops. Okay, that is I do experiments at delta P1, delta P2, delta P3, okay, like that. Okay, and then I calculate what is Rm, okay, and what is alpha. That is essentially basically doing, I do a constant pressure filtration, I do T versus V versus T by V versus V, right? And then I get a straight line. I look at what is the slope and the intercept, and from the slope and the intercept I can actually calculate these things. Therefore for a set of delta P conditions I can calculate what is alpha and Rm, and if alpha is independent of pressure drop, that means no matter what is the pressure drop that is maintained, if alpha remains constant, then I can say that the cake that is formed is incompressible. However, that need not be the case. That means if I were to plot alpha for delta p, if it remains constant, that means it's a incompressible cake. Okay. However, that need not be the case. And one of the empirical equation that has been developed to kind of capture how does the alpha, which is the filter, which is the specific cake resistance varies as a function of pressure drop, is alpha goes as alpha naught into delta p to power s, which is an empirical equation which is obtained by doing a lot of experiments. And this alpha and s are empirical constant, and s is something called as a compressibility coefficient. Okay, it tells you how compressible or how incompressible the cakes are. If s is equal to 0, that means it is a incompressible cake. However, typically people have found that the alpha takes a value from 0.2 to 0.8 depending upon what pressure drop you maintain, and more closer this value is to 1, that means it is highly compressible. More closer it is to 0, that means it is less compressible. And for alpha is equal to 0, I can say that the cake is completely incompressible. Therefore, this particular framework gives you a way of calculating both the filter cake resistance and the filter medium resistance, which in turn can be used as a method for identifying the nature of the filter cake that is essentially formed during the course of filtration. Okay. Maybe I'll stop here. So I'll continue with talking about constant rate filtration and the continuous filtration in the next video. Thanks.